All right, guys, I got a question here from chapter 20, my first one from chapter 20. And of course, it's out of the university physics book, so it's a real hard one. And it is a doozy in the sense that it's a step up on something that we didn't really cover in the college physics book, or did we really talk too much about it. So this problem's going to take a lot of your thinking, a deductive reasoning to kind of work out. And so follow along with me if nothing else. Here's kind of your author's thinking. Let me hold off on the problem for just a second and just come to your textbook. We were introduced to the current, and we said the current was a certain amount of charge that flows in a given amount of time. Okay. And what we did is we had this little picture of a wire. Maybe the wire was kind of a cylinder shape or a circular cross section, and the current would kind of flow through here, and so kind of like water in a pipe. We just said this is the total charge that flows through some area. We never got into more details about, well, maybe the stuff in the middle is flowing faster than the stuff on the edges. That's what happens in a water pipe. You might remember going back to Physics 121, and when we went from no viscosity to some viscosity, and we had a picture in the book, I remember looking something like this. The water was flowing up a pipe, and they gave kind of a cross-sectional profile, and they said the stuff in the middle was the fastest, and the other stuff tapered off. And that's because there was rubbing along the surface. There was a viscosity. Well, the same type of thing can happen with our electronics. Now, we don't really have a viscosity, and so some very other interesting things could happen. Actually, the current profile can be greater on the edges than in the middle, and so the current profile might look something more like this. That happens a lot. But it could also happen like the water happened. There could be kind of a resistance on the surface. But like I said, and so let me not go into detail about the current profile, but the current profile can be much more complicated than just equal, like we had the flow of water, equal, all speeds were equal across the diameter of the pipe. And of course, that's what you get in a perfect non-friction world. But with viscosity, that's just not the case. And then you have adhesion forces. So anyways, what this problem is kind of asking you to do is to take into effect that maybe you don't have the same flow rate everywhere across your wire. Now, to make it a little easier on us, they gave us a square wire. And if you look here, they say, consider the current density. Now, maybe that's worth mentioning here. That is the profile. That is what they're saying here is how much current do you get in a little small area. So in other words, they're saying instead of looking at the total current, because like I said, the total current may not be equally for all parts. Maybe most of the current comes from the center, or maybe most of the current comes from the edges. And so they call this J the current density, and it would be the current in a given area. Now, it would be a small amount of current in a small amount of area. So maybe I should use my little calculus, because here's what I'm really saying is the total current then would be what you get when you add up all the current. And some of it, like I said, has a higher speed or a higher rate of current than other parts. And you can then give that current profile by calling it a current density. So this is the current in a small area, and then you multiply by a little area. That would be a little bit of current right there. And then if you add it up over your whole wire, that would be the total current. So this problem like I said, is probably going to hit you hard because we really didn't go into detail like we did for the flow of water. This, like I said, book is an advanced one. I would assume the book maybe talked a little bit about it. And so again, maybe like my other ones, maybe I got too overzealous when I saw this one. I thought, oh, this will be a good one with calculus, but it might be a little, maybe too much for this class. I don't know. This one's questionable. The other ones I did, I was definitely thinking, okay, yeah, too much. That was me trying to look for a good calculus one that was not too much. But this one's right on that borderline because even though we didn't do all this, this is very logically sound. I think you could put this together, putting together with your flow from Physics 110 and the difference between a non-viscosity and a viscous flow. And then putting together with your calculus. So it's asking a lot, but doable, I guess. And so if you were able to do some, great. If not, and you're just watching through the video, that's perfect too. You know, whatever it takes. But I do feel like I have to kind of give a little mini lecture here to say this is how you get the current. The current is you add up the profile over the area of the wire. Okay, so with that in mind, this is what we're going to do. What we're going to do is to find the current. And that's what it says. Find the current that passes through the face of this rod. And so we have a square rod. So the rod's really long, and we've cut it here. Looks like this is the x-axis and the y-axis and the z-axis, and they cut it. And they give us this equation. Let me use this. And in fact, it has an exponential term, if you will. They also use a little fancy symbol, but fortunately I think it's pretty obvious in the diagram here. They're trying to say that this K hat is this thing here. It is what you might call the z-axis. And so they're trying to say it flows out in the z direction. And that's perfect. So what I'm going to do is I'm going to find the total of all the current, but notice this is an exponential. And an exponential is looks like a positive number. And so if I were to look at the current density as I move out, and then there's the variable x. So as I move on the x-axis, it looks like my current gets bigger, 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 bigger. And then, of course, maybe then I get to position L. So as I read this math, they're saying here that the current is just some small value. In fact, you can see at x equals to 0. So e to the 0 is just J naught. So there's some current density in this area, and I'll color it in. And by the way, I should point out in passing here, notice that the current density only changes as you move on the x, not on the y. So this little strip right here, all would have, if I give it a little width of dx, would all have the current density of just J naught, which apparently is 0.35. Okay. But then as I move out, and your author's trying to help you, he's got this kind of shaded green area. So this is his strip. But this strip may be represented in this graph maybe right here, so that would have a higher current density than any of the strips on this side of it. However, it's not as big as they're going to get for the strips over on this side. And so thinking of this as a bunch of strips, you can find the total current by saying, well, how much current is in one strip, and then add up all those strips. And so his picture is trying to help by saying, okay, let's look at this green strip right here. He's trying to say it has a height of L and it has a width of dx. And so if you think about this integral right here, where the current is the integral of the current density times dA, the dA is a small amount of area, and that would be this area of this strip. So let me just, say this right here without the integral. Okay, just the J times the dA, as we talked about up here, right? If I take the J times the dA, I'd get a little bit of current. That would be the current that's in this green strip. That's why then I would have to integrate it to get the total current. So let me not do the integral yet. That's going to come, but let me just put in these two values. I know the equation for the current density. They say it was J naught e to the AX. Okay. And the little bit of area, they helped me out here with this green strip, and they told me the area would be L by dx. So this is L by dx. Ah, nice. And now I can actually set my limits. I could say, okay, so what am I going to do? I'm going to maybe add up the first strip, and so there x would be 0, and each strip x would get bigger and 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 bigger until I got to L, and so the limit would be L, so 0 to L. Okay, and so now I can actually do the integration, and like all of our integrals, the very first thing to do is to look for anything that is a constant and pull it out. Okay, nice. Then we can do our integration. Now I'm not sure if this semester we've done any integrals with an exponential. Fortunately, those are easy. Now, maybe not as easy as a power function one, but you know that, if you take a derivative, and I'll just do it in reverse. If I had e to the ax, and I took its derivative, you get e to the ax, and then the chain rule gives you an a. So if we're going in reverse, I guess we would say something to this effect. I'll bring then and say, all right, had we not had that a, in other words, if we had e to the ax, and I'll just say over a when we took the derivative, we would get e to the ax, and then the chain rule would bring down an a, but remember it's also over an a, and so we just get e to the x. So there's our answer. So if you take the derivative of this, you get that, which means then if you take the integral of this, you get back to here. All right, so this would be e to the ax over a. And like I said, maybe the best way to do it is to check by taking the derivative of this. Now that you say this is the integral. And of course, I just did. You take the derivative of that, you get your e to the ax. Okay, good. And then I can put in my limits of 0 to L. All right, so we've got J naught L. Maybe I'll put the A here. And then we've got our e to the AL minus okay, already factored out the a. Okay, then we have e to the 0, which is 1. So J naught L over a, e to the AL minus 1. And I was hoping to squeeze it on one page, but I'll save the yellow page and take this, and no, maybe I'll, here I got a yellow page with very little writing on it, so I'll use that. Okay. So I would have this J naught, which in this problem they give me. The J naught is 0.35. The L length of L, they've got it as 3 centimeters. So I will put it as 0.03. And maybe over here I'll put my units. Remember the J naught was amps per square meter. And then the L is in meters, okay? Then all over this A, and this A is this crazy thing, 2.1 times 10 to the negative 3. And it would be units of inverse meters, according to this. Okay, and then my exponential, which would be E, and I didn't give myself enough room, so let me just write it as AL minus 1 for a second. But let me point out then that wouldn't be any units, because this has to be unitless to go with the 1, which actually is perfect, because this inverse meter can be put upstairs there, and then these square meters can cancel off, and we're left in units of amps, and that should be expected. But this number is A times L, and then raised to the exponential. So let me take A, what was A? 2.1 times 10 to the negative 3, times the L, which was the 0.03. All right. So if I then go E to that last answer, and then I subtract 1, that's what all this is. So then times 0.03 times 0.35 divided by 2.1 times 10 to the negative 3, coming out to be 3.15 times 10 to the minus. Now it says minus 4. I'm going to write it as minus 1 and a minus 3. I like the minus 3 because that's milliamps. That's a very common unit we use a lot. An amp is, by today's standards, unless you're running something with power, but all of our electronics, milliamps are a much better unit here. Then 10 to the negative 1 would just be 0.315. All right, and that's it. Hope that helps.